Alright class, so as I mentioned on the first day, there's sort of a few probability topics that we need to know for just small parts of the class. I know a lot of you have probably already taken a probability course, but even those that have, this is a nice review. And when we bring them up in class, I'll sort of remind you of them as well. But this kind of just to introduce you to the idea, and that way you can come back and rewatch it if you need to. So kind of just first starting with some definitions here. The first one there was just called a random circumstance. And this is just one where the outcome is unpredictable. And that's a lot what we work with in statistics, is we're trying to predict things that we don't know the outcome to. So that's one of our big goals. The one thing that we need when we have a random circumstance is to know the probability of it. So this is our likelihood or the chance of a certain behavior, and this is what we're always talking about, like long-term frequency. So what I mean by that is when we know when we flip a fair coin that overall 50% of the time it should be heads. That's what we mean by the long term. It's kind of over the long haul. But that doesn't mean that every time I flip it twice I'm going to get one heads and one tails. So probability is that likelihood over the long run of things. So some kind of basic information that we need to work with here is to understand some basic rules of probability. So the first one is, and this is an important thing when we start calculating them, is that a probability has to be always between 0 and 1. And so another way that we write that is that 0 is less than or equal to the probability of any event. E is just any event that we're talking about. That could be, flipping a heads. It could be passing a class, like whatever we're trying to calculate the probability of. And it has to be some number between 0 and 1. And it can technically include 0 or 1. Actually, there could be a 0% chance of something happening. There could be a 100% chance of something happening. We, of course, generally work with more numbers that are in between 0 and 1. And overall, when we talk about summing all probabilities, the probability that something has to happen is equal to 1. So if I sum, which that's what my cap sigma means, is just to sum things up, or to add them all together, all the probabilities of all my events, I'm going to get 1. So something has to happen. So if I look at flipping a coin, the probability that I get heads or tails is going to be 100%, because those are my only two things that can happen. Since we're numbers between 0 and 1, kind of understanding what those extremes mean is important. So if I actually get a probability of 0, this would technically mean that that is an impossible thing to happen. That'd be, for example, if I flip a coin and getting a goat, right? That can't happen at all. If I were to get a probability of 1, this is what's called a certainty, that it's going to happen. Okay. Now again, of course, very seldom do we actually have those extremes, but we talk about the extremes to understand what it means to be close to them. Right, so if I get something close to 0, this is going to mean that it's very unlikely to happen. Whereas if I get something close to 1, it's going to be very likely to happen. So kind of first is understanding those extremes. The other thing we're going to introduce here that we're going to need here shortly, actually in the single proportion notes and for a little bit further, is a few different counting techniques. Now, although we're only going to use a couple in our class, I'm going to introduce a few different ones just so you actually understand that there are different ones that you might see. So we're going to have a lead-in example here. So we're looking at Applebee's offering their 3-course combo, which generally means you get to choose 1 appetizer, 1 entree, and 1 dessert. So let's suppose they offer 2 different appetizers, 3 different entrees, and 2 different desserts. How many different meals could be ordered? So what I'm going to start with is we'll start with our appetizer. Right, and so for my appetizer, I could choose appetizer number 1 or appetizer number 2. Now when I move on to my entree, it doesn't matter what I chose for my appetizer. I can still pick any of those 3 entrees. Right, so I can choose entree number 1, entree number 2, or entree number 3. Same thing if I pick appetizer number 2. And then finally, the best part of the meal, of course, is dessert. And so it doesn't matter which appetizer and entree I've chosen, I can still choose either of those 2 desserts that's left. So I could choose dessert 1 or 2 here, dessert 1 or 2 here, dessert 1 or 2 here, and keep doing that for all of my possible appetizer and entree combinations. So now try to figure out, well, how many total meals are there? Well, I could use appetizer 1, entree 1, dessert 1. Appetizer 1, entree 1, dessert 2. And so I'm just looking at all these different combinations. So what that turns out to be for me here is just how many total branches did I end up with here. So there's going to be 12 possible meals that I could order. And so what I do here is what's called a tree diagram, which can be very useful to kind of list out different things that can happen. But sometimes as they get bigger, it's pretty difficult. So imagine if I were to do the same thing with 6 appetizers, 7 entrees, and 4 desserts. That tree is going to get pretty messy pretty quickly. So we want to understand how this principle works. Like, how could I come up with this 12 without actually having to draw out the tree diagram? And so this first way is what's called the multiplication rule. And for those of you that have seen this before, it's important to make sure that you understand when to use it. So a task consists of a sequence of choices, kind of like what we have here. Choose an appetizer, choose an entree, and choose a dessert. There are so many selections for the first choice, so many selections for the second choice, and so many selections for the third choice, and so on. But what's important about using this multiplication rule is your first choice doesn't impact your second choice. So what I mean by that, if you got a certain appetizer that forced you into a certain entree and you didn't have any choice when you went here, the multiplication rule couldn't be used. But how we use the multiplication rule is that then the total number of ways that you can do that sequence of choices is just to multiply your different options together. And if there are more, we keep going there. So for up here, if we look at it, so we had 2 appetizers, 3 entrees, and 2 desserts. And if I multiply those numbers, we get our 12 that we saw from our tree diagram as well. So let's see how that works with a couple of examples. So how many options would be possible for this new 3-course combo that I talked about here with the 6 appetizers, the 7 entrees, and the 4 desserts? Right, so for my appetizers, we now have 4 choices. Oh, sorry, I might have missed with that. 6 choices there. And then we have 7 choices for our entree. And we have 4 choices for our dessert. So then I can just multiply my different numbers together and find out that I would have 168 possible 3-course combos. Another example, how many different sets of initials are possible for first and last name? Well, how many different initials could you have for your first initial? Right, there's 26 letters in the alphabet. How about for your last name? Doesn't matter what your first initial is, right? You can still have any initial for your last name. So we just multiply those together to find out there's 676 possible outcomes for sets of initials for first and last name. And then here, out of our 8 swimmers, how many different ways could we get a gold, silver, and a bronze medal? So imagine we're watching the Olympics here. So we have all 8 swimmers in the pool. How many of them can touch first? 8. Now how many can touch second? Well, the person that got gold can't get both medals, right? So there's only 7 people left that can do the silver medal. And once those 2 have touched, there's only 6 left that can touch for the 3rd medal of bronze. So now I'm going to multiply those numbers together to get 336 possible ways. To talk about our other ideas of counting techniques, you first need to be comfortable with the factorial symbol. Even though you don't actually have to write these out using the factorial symbol, it's still a good thing to know what it is. So n factorial means that you take n, times n minus 1 times n minus 2 all the way down until you get 1. So for example, if you had 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. That would give me 720. So that's what it means to have a factorial. Okay. So this introduces, we need this factorial for what's called permutations and combinations. I have these two together because they can be confused. So we're going to look at them both together before we actually try to apply one. So a permutation has order involved, whereas a combination, we don't care about the order. And we'll see this with a couple examples. So for example, when you enter in your garage code to try to get in, right, but I have to enter in 4 numbers, I have to put them in the right order to get in. I can't put those same 4 numbers in any order I want and still get in. So there's sometimes where things ordering matters and sometimes it doesn't. Both of them start with a total of n objects that are different from each other. And we're going to select R of them. And it says where repetition is not allowed. So basically, once I select one thing, I can't select it again. So those are important things. So what's true about both of them is we have n distinct objects. We're going to choose R of them. And sometimes how we rephrase this is we're doing it without replacement. So that means that as I take some out, I'm not putting them back in. It's like I can't be selected more than once. Again, so the main difference is a permutation, we worry about order. A combination, we don't. So let's see how these ideas apply to a problem after we talk about the actual formula. So, and the reason why I said you might not actually need to worry about the factorial is a lot of calculators have these keys on them. So the NPR button does a permutation, whereas the NCR button does a combination. And so this is what they look like. So the number of permutations is n factorial over whatever n minus r factorial is. And I will write these out for our first couple of examples. Versus the number of combinations is n factorial over the n minus r factorial, just like what you see up here, except for it has this additional r factorial, which basically gets rid of your duplicates of where the order is not mattering. So let's look at a couple of examples. So suppose we have a group of 6 individuals, so they'd be different. How many different ways can they form a 3-person committee? So I usually list out these lines, which you've probably already seen, but it helps me figure out, are those lines different? If I'm the first person chosen versus the second person chosen versus the third person chosen, does that make a difference? So does order matter? Nope. I mean, if I'm on the committee, I'm on the committee. And I would need to know what my N is, my total number of people that I have, what my R is, and how many I'm choosing, which is 3. So because of all this would lead me to a combination. So I'm going to do 6 combination 3. And if you're hitting this in your calculator, you're first going to hit the 6, then you're going to get your NCR button, and then you're going to hit 3 before you hit equal there. Which this is n factorial over n minus r factorial times r factorial. So that's what it would look like when I wrote it up. So then simplifying, this is 6 factorial over 2 different 3 factorials, which would simplify to 20. Now, if instead I was looking at picking a president, a vice president, and a secretary, again, the first thing I'm going to ask myself is if order matters. Or in a sense, if you pick the same 3 people, can I rearrange them in a different way and it actually is different? So here, that answer is yes. Right? Because, for example, I could be president with the 2 other people serving those other roles, but I could also be vice president with those 2 people serving in those other roles. Right, so which spot I am is different for me. I still have 6 people I'm choosing from, and I still need 3 of them. So doing our actual math over here, this is going to be a 6 permute 3, which just like with your calculator here, this is how you're hit the 6 first, then the permutation button, and then the 3, which is n factorial over n minus r factorial. So what you see when you compare the two, right, is that this number is going to be bigger than this one up here because I don't have this extra number I'm dividing by. So this one turns out to be 120. So now we have a little idea how to do that. We're going to actually how to calculate a probability using some of these techniques. So we have if an experiment has n equally likely outcomes, and if the number of ways an event E can occur is m, then I'm just going to take my number of ways that event E can occur, which is m, over my total number of possible outcomes, which is little m. But again, it's important that they're all equally likely in the sense that we're drawing things randomly. One person is not more likely to be selected than the other, like in our example. So we're going to kind of start with a similar setup with a little bit more background here. So we have 6 individuals, 4 of them are men, and 2 of them are women. I'm going to choose my 3-person committee from this list of 6. Right, so it's a very similar setup to what we had before. Right, I have an n of 6, an r of 3. Since we're just picking that 3-person committee again, order does not matter. Right, so first just making sure the setup sounds okay. So all this first up is making me think combination. Suppose I want to find the probability that the committee is all male. So m is going to represent the number of ways it's all male, versus n is just the number of 3-person committees we can make. So usually the n is usually easier to do. This is not being specific at all. This is just our 6 combination 3 that we already had from the previous page, right? We have 6 total people. We're going to choose 3 of them. Order doesn't matter. That's going to be our 20. Now on the top, with our m, we have to be specific. So it's got to be all men. So how many men are there? There's 4. How many of them do we need to choose? 3. Again, will the order matter that I pick them in? No, right? So if it's the same 3 men, it's the same 3 men. So that's just going to be a 4 combination 3 to give me 4. So then my probability that I have an all-male committee is going to be 4 out of 20, which is a 20% chance of that happening. For number 2, we're going to figure out the probability that the committee includes Lisa. So m is the number of ways to include Lisa. N, notice, is still the number of 3-person committees. So that's still going to be our 20 that we had from above, because I haven't changed the setup at all. M is where I gotta start thinking now. So I know I have 3 spots. And to find M, what I know is that one of those spots includes Lisa. It doesn't matter which spot I put her in, right? I'm just picking a spot to put her in. So how many spots are left? Well, there's 2 spots left. How many people left to choose for those spots? Right, there's only 5 people left because I can't have Lisa serve on the committee twice. I only have 5 people left here. Order is not going to matter. This is going to give me a 5 combination 2 for that, which gives me 10. So the probability that we include Lisa is 10 out of 20, or 50%. And I like this example because it kind of makes intuitive sense. There are 6 total people, a 3-person committee. There's a 50% chance to include in any individual person because that's what 3 out of 6 is. So it kind of makes intuitive sense. For number 3, we want to figure out the probability that includes all females. So M is my number of ways that it's all women, females. I'm still picking my 3-person committee, so my N is going to be 20. Alright, so I have 3 spots. How many women do I got? I only have 2. Right, so if I put Brooke here, I put Lisa here, I have to pick a guy. Right, if I only have 2 people, I can't pick 3 people from 2 people. So there are no ways that I can have a committee that's all female. So then the probability that it's all female is 0. Right, there's no way, it's impossible for me to be able to do that. Right, another example is the probability that the committee has 2 males and 1 female. So as you can probably see my pattern here, my N is going to be 20 because I haven't changed that. M is the number of ways to have 2 men and 1 woman. Alright. So let's first focus on the men. How many men are there? 4. How many of them do I need? 2. Order doesn't matter, and me picking them. Same thing for women. How many women are there? 2. How many do I need? 1. So this is 6, and this is 2. Here's where we struggle a little bit. It's I need to do something with these 2 numbers. I either need to add them, subtract them, divide them, or multiply them. Right? I've got to do something with these numbers. So what do I have to do? This is actually now where the multiplication rule applies. Right? So I'm going to pick 2 men, and then after I do that, I'm also going to pick a woman. Right, I'm doing this sequence of events here. So this actually is going to be a multiply, giving me 12. So the probability of having 2 men and 1 woman is going to be 12 out of 20, which is 60%. Alright, for our next example, we're going into the 3-course combo one here. So we have 6 appetizers, 7 entrees, 3 of which are pasta, and 4 desserts, 2 of which are cheesecake. Now first going back, right, we already found the total number of 3-course combos that were possible. All we have to do now is figure out what the actual problem is asking. So we want to find the probability that we don't have pasta for our entree. Alright, so that's all I'm trying to find. So how many different appetizers can I pick from? All 6, right? Those aren't pasta. 7 entrees, 3 of them are pasta. So I have 4 that I can choose from. And I have a total of 4 desserts because none of those are pasta. So I'm going to be able to choose all 4 of those. Again, multiplication rule, since I'm selecting an appetizer and an entree and a dessert, to give me 96. So the probability of no pasta is equal to 96 out of 168, which we'll also notice simplifies to 4 out of 7. Total number of entrees, total number that aren't pasta. Right, so it didn't affect my appetizer or my dessert at all, so it really had no effect here on that part of the probability either. Now for number 2, we're looking at the probability we have both pasta for the entree and cheesecake for the dessert. So still, total number of 168 possible 3-course combos. And we've got to have pasta, and we got to have cheesecake. Alright, so if I have to have pasta and I have to have cheesecake, how many appetizers can I pick from? Well, the pasta and cheesecake had nothing to do with my appetizers, so I can pick any of my 6 appetizers that I want. Now, how many entrees can I pick? Well, it has to be pasta. 3 of them are pasta. So I have 3 different entrees I can pick from. For my dessert, I want cheesecake. Only 2 of those are cheesecake, so my option there is going to be 2. Again, multiplying, since we're choosing one from each group here, to give us 36. So the probability that we have pasta and cheesecake is 36 out of that 168, giving us a little bit more than a 21% chance. Now again, I probably did more in this video than I needed to for your understanding, but it's good to have more knowledge than what you need. The important things that you're going to see from me. The biggest one you're going to see from me is you're going to see combinations. That one's going to show up a lot. More specifically, you will see combinations written a different way. You'll also see it written as this NR that kind of looks like a fraction, but there's no line between it, and so you'll kind of see that quite often. And really the big ideas here with multiplication, we're all just kind of understanding when we can multiply numbers, as well as just understanding what probabilities are. So it's kind of like the big things that you want to take away from this video.